Hello, my good friends. Let's continue with thermodynamics. Um, this unit. Here's where I start. Each eating up some valuable seconds, but I'll try anyways. I'll just tell you. One of the tricky things about this unit, as you've seen so far in the first few problems, is that in a lot of cases there isn't just one way to solve a problem. There are lots of ways to do it. The equations end up being pretty simple. But as you've seen, hopefully, in fluids, sometimes when the equations look the simplest, there's the most physics involved, the most understanding of physics involved. Hence, I love this unit. Um, so we left off last time talking about, some generic processes in which, in this case, on the left, a gas expands. In the middle here, the gas is compressed. Maybe it's a whole cycle of a process. We can find the net work by finding the area of that enclosed loop. So these are just, general, here is a process. Right? We're going to talk in the next, really here in this slide about 4 specific processes, okay? And ones that you need to be familiar with, need to be able to recognize both on what we call a PV diagram, these graphs, these pressure versus volume graphs are what we call PV diagrams. So you need to be able to draw them, recognize them, and make some assumptions based on the presence of one of these or hearing about one of them. Okay, so there's one we'll call an isobaric process. Well, iso, right? These all mean constant. Iso means the same, right? Like an isobar, right? An isobar, we drew isobars in our static fluids little investigation. And those were lines where pressure was constant. So if we want to draw a constant pressure thing, it's going to be like this, right? Well, whatever that pressure is, this remains constant. Okay, this could be, so let me just write this, constant pressure. Right, this could go to the right or to the left. It could be an expansion or a compression, but as long as pressure is constant, that's what we call an isobaric process. All right, let's go down here. Isochoric, you'll also see this as the easier one, isovolumetric. That makes it easy. Constant volume, right? That will look something like this, whether it's up or down, whether pressure increases or decreases. As long as volume stays constant, that's what we call an isochoric or isovolumetric process. Okay, isothermal, a process that occurs at, constant temperature. Well, this one's a little harder to draw, but, well, it's not really, but if we write it like this, or if we look at the equation of state that relates pressure, volume, and temperature, this says that if temperature is going to stay the same, well, if pressure goes down, then volume goes up. Or if pressure goes up, then volume goes down. It's an inverse relationship. All right? We can actually do it pretty carefully if we do something like this. Let's take a data point, right? Okay, there's a volume and a pressure. Well, if pressure gets half as big, then volume gets twice as big. That's that inverse relationship, right? Let's cut this original pressure in quarters. Well, that means the original volume gets 4 times as big. Looks about like out to here. And then, cut that in half. Then we double this one, and we go out, say, to here. So we can draw without too much trouble an actual mathematical inverse relationship. It looks flat here at the end. It shouldn't. All right, it never actually flattens out. Okay? And then there's an adiabatic process. This is a process where no energy is transferred. Let's say transferred. Either into or out of the system. And we would say here, no heat, right? Heat is that process by which energy is transferred. The tricky thing about adiabats and the adiabatic process is they look kind of like isotherms. They're just like steeper, more severe. Again, it doesn't really curve up here at the end. Okay? Okay? Yeah, there it is. If I can move this stuff. Whoops. Yeah, adiabatic curves are always steeper than, son of a, than isotherms that pass through the same point. Okay. Now, so what's the difference? You know, what's the difference between something that happens at a constant temperature and something where there's no energy transfer? Well, we can boil it down into what we call the first law of thermodynamics. And here's the first law. It says that when a gas is heated, or really we're saying when energy is transferred to a gas, well, here's what the gas will do. It'll take that energy and use it to either increase its internal energy, which we know means or is closely tied to temperature, or, well, it can do one of two things, or it can actually do two things. The energy will either go to increasing the temperature of the gas, or it can go to making the gas expand, or it can do both. All right, so you add energy to a gas, it's going to increase in temperature, or expand, or both. Hopefully that makes sense. It does to me. But I teach physics. So, in an equation form, well, we actually write it like this. We write it as delta U is Q plus W. Now, this statement of first law in green more sort of says that if you add energy, it can do this. It can either increase the temperature or the gas will do work. Notice that the signs would be different if we rearranged and solved for delta U like we do here. So the sign convention that you choose for your equation and for your sort of, really the equation that you use for the first law, the sign convention is really important. Not everyone uses the same sign convention, but the one that AP uses and the one that we use are, we're going to be very specific about that, I think, on this slide. So delta U, right, we've talked about this. It is defined to be a change in system's internal energy, right? But remember, we said that U is 3 halves nkt, or 3 halves nRT. So we know that internal energy and temperature are very closely tied. All right, so when you think about delta U, internal energy, or change in internal energy, think about change in temperature. Think about change in temperature. They're not the same exact thing, but they are proportional. Okay? Q. We've defined this as heat, or energy really, energy transferred to the system. Okay? Fair enough? And W, by definition, is work done on the system. All right, these are our definitions of, this means as opposed to here, Q could be energy taken out of the system. W could be work done by the system. We're defining it to be as what you see here. So when, this is super duper important, when are each of these positive, negative, and or 0? Well, let's see. When's delta U positive? Well, delta U is positive if temperature increases. Or if, really, if delta U increases. If U increases, right? If internal energy increases. But really, we can sort of think about it, easier to think about, I think, in terms of temperature. So if temperature decreases, or internal energy decreases, delta U is negative. When is delta U 0? When is delta U 0? Well, if internal energy doesn't change, or if temperature doesn't change. Well, it's 0 if you see the words, or the word, isothermal. In any isothermal process, delta U is 0. Okay? Okay. So let's see. Now, Q. Q is positive if energy added to the system. Therefore, negative if energy removed from the system. And it's 0. Q is 0 if there's no energy transferred at all. That's what we call an adiabatic. process. Okay? Okay. And work done on system. We say that it's positive if work is done on the system. All right? Well, when we do work on the system, we say that the gas is compressed, or during any compression. All right, if we are doing work on the system, W is positive. Okay? If the gas expands, we say that work is negative. Right? Compression is work on. Expansion is work by. So lots and lots of word clues in these kinds of questions. Tons. All right, you got to look for those things like, added, removed, on, by, stuff like that. And work is zero if, well, here's a big deal. Work is zero, we know, if things don't move, if there's no motion. Well, the only process that we saw where nothing moved is if the volume of the system stays constant. That little piston, right, this is all about, we're always sort of thinking about, or hopefully should be thinking about, pistons in cylinders that are able to move up and down. Well, if this thing does not move, then there's no work done. All right, and that's what we call an isochoric. Isochoric, yeah, sure. Or isovolumetric process. Okay? Fair enough? This will be a big, big reference for you for the next couple of days at least. You'll probably end up going back to that a bunch. All right? The sooner you sort of have that, the sooner you're comfortable with these sign conventions, the better. Quick. Okay, so let's look at some examples. Here's one. These are what we call first law examples. A gas in a container with a piston expands isothermally. Ding, ding, ding. There is a clue. Isothermally. This means that delta U is zero. No change in internal energy if temperature stays the same. A quantity of heat, 10 to the 5th joules, is given to the gas. Okay, that means that Q is positive 10 to the 5th joules. What's the work done by the gas? The work done by the gas. Well, let's see. We can go to first law and say that delta U is Q plus W. And let's see. Well, delta U is 0, so Q, negative Q, equals W. So work is negative 10 to the 5th joules. But for us, work, W, is work done on the system. So if the work done on the system is negative, then the work done by the system is positive 10 to the 5th joules. So let's think about this, right? How could this happen? What would we be talking about here? Well, we'd be talking about a system like this, cylinder, piston, and we, let's see, we add energy to the system, right? So you got a gas in here, right? And what we do is, I don't know, light a candle underneath this. Here's a flaming candle. Little holder. Isn't that nice? It should be colored, of course. Flaming candle, right? And we add energy to the system. Well, if the temperature of the system is going to remain constant, the only way for that to happen is if this piston rises up to here, right? Now the gas has done work. The gas has expanded. So therefore, the work done by the gas is that much. What do you think? Good? Next. The gas expands adiabatically. Ding, ding, ding. Adiabatically means Q is 0. Well, its temperature increase or decrease? Love it, love it, love it. So let's see. If delta U is Q plus W and Q is 0, another word clue. Expands. Expands. That means that W is, let's see, positive or negative. Expands. That's work done by the gas. So that means this is negative. So that means delta U must be negative also. So temperature must decrease. What do you think about that? Okay? Number 3. Come on already. Monatomic gas kept at constant pressure, okay. That doesn't really tell us anything about first law variables, but there's an initial volume, an initial temperature. Gas is compressed, constant pressure down to that. Find the work done. Well, these work ones are, now there's at least another way to find work. We can do first law, but we don't know anything about, we do know change in temperature, but we don't know anything about Q. So the other way to find work done, especially when you see this, constant pressure, this is a P delta V. I know we haven't talked about that yet today, but it is something we talked about last time. All right. So there's P delta V for work. We got to make sure that we're in cubic meters. We are. We're in pascals. We are. That's good. So work is going to be, let's see, 3 times 10 to the 6th pascals. And the change in volume is from 0.1 to 0.08. So that's 0.02 cubic meters. I hear you saying, wait, it's negative, it's negative. Yeah, I don't worry about signs until I'm sure what the question was really asking. So let's see, that's 2 times, how about this? That's right, there's 2 times 10 to the negative 2. So multiply those together and we get 6 times 10 to the negative 4th joules. And it's compressed, so that's work done, well, on the gas. I'll leave that as positive. Okay? Got that? Compressed, for us, work is positive. It really matters, that sign really matters when we want to do this. If we want heat removed, the only way to ever find heat removed Q is to do first law. That's the one nice thing. There's only one way ever to find Q, and that's what we call this first law. All right, so Q is delta U minus W. Delta U. Check it out. So lots of ways to do delta U. Here's one of them. Well, we know that U is, well, 3/2. What do we know? Monatomic gas. We don't know how much of the gas there is. It's one interesting thing. Oh, well, how about this? No? Ooh. Hang on, folks. So this is perfect. I just sort of illustrated my own point here because I'm like, man, how do we do this? Sorry, how do we, do this one? Because I know that U is 3/2. Whoops, 3/2. For example, NKT, or U is 3/2 nRT, and I have this temperature. But I don't know how many moles or how many particles. Well, so what I have to be able to recognize is that NKT is PV. Well, and so is little nRT. That's PV. So that means that we can write U as 3/2 PV. And I do know pressure in 2 different volumes, but check it out. We're looking for a change in U. So I can do P times a change in V. How about that? Lots of ways to skin these cats, solve these problems. So let's see, there's our delta U. So our Q here is going to be, well, check this out. In this case, we have delta U is 3/2 P delta V minus our W, which was P delta V. That ends up being 1/2 P P delta V. And if work, P delta V, was 6 times 10 to the negative fourth, then Q is 3 times 10 to the negative fourth joules. Okay? You got me? You all right? Okay. Now, these next ones are allow us to look at each kind of different process and figure out the signs of things. Great little exercise to really sort of try to review each one of these processes. Sorry, back one? No, forward one. Okay, so I'm going to do 2, and I'll leave you to do 2 for homework. All right, so this, let's see, this process here, what are we looking at? This is called, well, this is a constant volume, right? Volume stays at this, value. Volume stays at that value. Constant volume. I don't even know. I think they call them isovolumetric more than they do isochoric. Don't quote me on that. Okay, so what can you tell about anything? We're looking for signs of things here. This is isovolumetric. Well, here's what I know. In isovolumetric, nothing moves. That means work is 0. How do I know nothing moves? Again, we're talking about a cylinder with a piston in it that can slide up and down, frictionless, blah, blah, blah. Well, isovolumetric means the volume in here is constant. And that happens if this thing does not move up or down. Therefore, if nothing moves, no work. Okay? Now, here's where we can apply what we just did in the last page. We just said that delta U is 3 halves times, well, let me go to this. We said that U is 3 halves PV. All right, so delta U, this will become one you'll use a bunch, is 3 halves really times the change in the quantity PV. Right, you put a delta on one side, you put a delta on the other. So what happens to the quantity P times V? Well, the product P times V starts at this pressure and that volume. And then later it ends up at this pressure and that volume. So the quantity PV increases. Therefore, delta U is positive. And if delta U is Q plus W and W is 0 and this is positive, well, then that means that's positive. Which hopefully makes sense, right? Nothing in the gas moves. We're not compressing. It's not expanding. But if we want the temperature to go up, how do we do it? Well, we add energy to the system, right? Put that candle underneath the what do you call it? Underneath the piston, the cylinder. What happens to temperature? It increases. I would call this an iso. I'll change to isochoric. Isochoric heating. Right? Heating, for me, talks about Q. Right? Maybe no surprise, but if we look this way, the next one, well, work is still 0. Nothing moves. Still isovolumetric, isochoric. Right? Well, like we said, delta U is 3 halves delta quantity PV. It goes from a big pressure at a volume to a small pressure at a volume. That means that delta U, or well, the quantity PV decreases. Delta U is therefore negative. And using First Law, that means that Q is negative. What happens to temperature? Well, it decreases. Again, because, what's going on with that? Decreases. Because delta U is negative. I'd call this an isochoric cooling. Rare that you'll have to actually, someone will say, draw me an isochoric heating. Rare? I don't know. I should make you do it. But it's rare in real questions. And by real questions, I mean AP questions. One more, and then I'll let you go. What's constant here? This is constant pressure. We call that what? Isobaric. Okay, so anything, something here, anything zero? I don't think so. It's not an isotherm, it's not an adiabat, and it's not a constant volume. So let's see. Well, you can start in one of two places. One is here. The sign of work, I think, is usually the easiest thing to tell. This gas expands. It goes from a smaller volume to a larger volume. The gas expands. That means, so this is an expansion. That means work by the gas. That means negative. Yeah? It's okay? Okay. Remember, the only way to ever find Q is to use the first law. Delta U is Q plus W. So let's look at U, delta U. Well, again, if we say that delta U is 3/2 times the change in quantity PV, we go from this volume at this pressure to a bigger volume at that pressure. That means the quantity PV increases. That means that delta U is positive. Okay? So how does that happen? Well, the only way for that to happen is if Q is like really positive. And let's think about this. What's happening? We're saying that the gas expands and the temperature increases. Well, the only way for that to happen is if we, light a freaking blowtorch underneath the thing. All right, really add a lot of energy. What happens to temperature? It increases. I'd call this an isobaric heating. You could also call it an isobaric expansion. Nothing wrong with that. Expansion because the volume increases. Heating because energy is added. Yes? Yes. Yes. Here, perhaps no surprise, work is done on the system. It's compressed. Delta U, 3/2 times change in quantity PV. Well, the change in quantity PV is negative, or it gets smaller. So that is, that's negative. And so that means that, well, let's see. The gas, we did work on the gas. We compressed the gas, but temperature dropped. That means we took tons of energy out of the system. What happens to temperature? It drops. We call this an isobaric compression / cooling. What do you think? Huh? First law? Right? Okay, so you have two of these to do. This one and this one. This one and this one. Fill in the blanks, fill in the boxes, tell me what you call them. How do you know which one's which? Well, go back to how do you know which one's which. Right? Notice the change in the shape of the curves. Fair enough, people? Fair enough. I will see you on Monday. 29 minutes. Okay. See ya.